Good evening, and thank you for joining me for tonight's calm reflection on science and discovery. Whether you're curious, tired, or just looking for stillness, you've come to the right place. I'd love to hear where you're listening from, what time it is, and what the world looks like outside your window. If quiet science stories help ease your thoughts, feel free to subscribe. We've only just begun to scratch the surface of what's out there. Mercury has always been an enigma, a quicksilver world that darts across our sky like a cosmic messenger reluctant to be caught. The ancient Greeks actually thought they were seeing two different objects, calling the morning appearance Apollo and the evening one Hermes. It wasn't until they realized these were the same wandering star that they settled on the name Mercury, after the Roman messenger god with winged sandals, forever racing between the mortal and divine realms. How fitting that name turned out to be. Mercury doesn't just appear to race across our sky, it actually is racing, completing its orbit around the sun in just 88 Earth days. To put that in perspective, if you were born on Mercury, you'd have a birthday every 3 months or so. But don't pack your bags for a Mercury birthday party just yet, because this is where things get deliciously complicated and rather mind-bending in the most soothing way. You see, Mercury has what we might call a relationship status with time that's decidedly complicated. While it zips around the sun in 88 days, it rotates on its axis much more slowly, taking about 59 Earth days to complete one full rotation. This creates what scientists call a 3-to-2 spin orbit resonance, a phrase that sounds like it belongs in a cosmic dance manual, which in many ways it does. What this means is that Mercury's day, the time from one sunrise to the next sunrise, lasts about 176 Earth days. Nearly 2 Mercury years pass in a single Mercury day. Imagine living in a world where your afternoon lasts longer than 2 of your years. It's the kind of temporal puzzle that makes you grateful for Earth's rather sensible 24-hour rotation. But the truly remarkable thing about Mercury's motion isn't just its speed, it's the shape of its path. Like all planets, Mercury follows an elliptical orbit, but its ellipse is more pronounced than most. At its closest approach to the Sun, called perihelion, Mercury ventures to within 29 million miles of our star. At its farthest point, aphelion, it swings out to 43 million miles away. That's a difference of 14 million miles, a variation that creates dramatic changes in the planet's orbital speed. When Mercury is closest to the Sun, it's racing along at about 35 miles per second. When it's farthest away, it slows to a more leisurely 24 miles per second. Though let's be honest, 24 miles per second is still rather brisk by anyone's standards. This variation in speed is a beautiful demonstration of Kepler's laws of planetary motion, those elegant mathematical relationships that describe how planets sweep through space like cosmic pendulums. Johannes Kepler discovered in the early 1600s that planets move faster when they're closer to the Sun and slower when they're farther away. And they do so in such a way that they sweep out equal areas in equal times. It's a bit like a figure skater spinning faster when they pull their arms in close, except instead of conservation of angular momentum, we're seeing the gravitational dance between planet and star. But Mercury's motion held an even deeper secret, one that wouldn't be fully understood until Einstein came along with his theory of general relativity. You see, Mercury's orbit does something rather peculiar. It precesses, which means the entire elliptical path slowly rotates around the Sun over time, like a cosmic spirograph drawing an ever-changing pattern in space. Most of this precession could be explained by the gravitational influences of other planets, particularly Venus and Jupiter, tugging on Mercury as it orbits. But there was a tiny discrepancy, a small but persistent difference between what Newton's laws predicted and what astronomers actually observed. Mercury's orbit was precessing 43 arc-seconds per century, more than it should have been, according to classical physics. Now, 43 arc-seconds might not sound like much, and it isn't. It's about the width of a human hair as seen from 10 meters away. But in the precise world of celestial mechanics. This tiny discrepancy was like finding a single wrong note in an otherwise perfect symphony. It suggested that something fundamental about our understanding of gravity was incomplete. For decades, astronomers tried to explain this anomaly. Some proposed the existence of another planet, closer to the Sun than Mercury, which they even named Vulcan. Others suggested that the Sun might be slightly flattened rather than perfectly spherical, but none of these explanations quite worked. Then, in 1915, Albert Einstein published his theory of general relativity, which described gravity not as a force, but as the curvature of space-time itself. When Einstein applied his new equations to Mercury's orbit, something beautiful happened. The theory predicted exactly the 43 arc seconds of extra precession that had been puzzling astronomers for so long. This wasn't just a successful prediction, it was a triumph of theoretical physics. Einstein later said that when he realized his theory explained Mercury's orbit, he was so excited he had heart palpitations for 3 days. It was one of the first major confirmations that our understanding of space, time, and gravity needed to be completely reimagined. Mercury's motion, it turned out, was showing us that space-time near the Sun is curved more than Newton's laws could account for. The planet isn't just orbiting through space, it's following the curved geometry of space-time itself, like a marble rolling around the curved surface of a stretched rubber sheet. The closer Mercury gets to the Sun, the more pronounced this curvature becomes, and the more its orbit deviates from the perfect ellipse that Newton's laws would predict. This discovery transformed Mercury from a simple planetary neighbor into a natural laboratory for testing our most fundamental theories about the universe. Every time Mercury swings around the Sun, it's conducting an experiment in general relativity, confirming Einstein's insights about the nature of gravity itself. But Mercury's wild ride around the Sun creates more than just theoretical physics lessons. It creates a world of such extreme conditions that it challenges our imagination. During its long day, when one side faces the Sun for 88 Earth days at a time, surface temperatures soar to over 800 degrees Fahrenheit, hot enough to melt lead. The Sun would appear more than twice as large in Mercury's sky as it does from Earth, a blazing disk dominating the heavens. Yet when Mercury's long night finally comes, temperatures plummet to nearly 300 degrees below 0 Fahrenheit. This is a temperature swing of over 1,100 degrees, the most extreme in our solar system. It's a world where the difference between day and night isn't just dramatic, it's literally the difference between molten metal and frozen wastelands. This extreme temperature variation is partly due to Mercury's lack of a substantial atmosphere. Earth's thick blanket of air helps distribute heat around our planet, moderating temperatures between day and night. Mercury has only the thinnest whisper of an atmosphere, mostly atoms knocked off its surface by the solar wind and micrometeorite impacts. This gossamer-thin envelope can't hold heat or moderate the planet's temperature extremes. The lack of atmosphere also means there's no weather on Mercury as we know it. No clouds, no rain, no wind, just the steady bombardment of solar radiation and the occasional impact of space debris. It's a world where the only sounds would be the vibrations traveling through the solid rock beneath your feet, if you could somehow survive to hear them. But perhaps the most fascinating aspect of Mercury's motion is how it affects the experience of sunrise and sunset on the planet's surface. Due to that complex 3-to-2 resonance between Mercury's rotation and its orbit, the Sun doesn't simply rise and set as it does on Earth. Instead, it performs an elaborate celestial dance across Mercury's sky. At certain locations on Mercury, an observer would see the Sun rise, then stop, then actually move backward in the sky before resuming its forward motion. This retrograde motion happens because Mercury's orbital speed varies so much during its elliptical journey. When the planet is moving fastest in its orbit, near perihelion, its orbital motion temporarily overtakes its rotational motion, causing the sun to appear to move backward against the stars. Imagine standing on Mercury's surface during one of these solar reversals. You'd watch the sun climb above the horizon, pause like a cosmic actor forgetting their lines, then slowly retreat back toward the horizon before resuming its journey across the sky. It would be like living inside a celestial clockwork mechanism, watching the gears of orbital mechanics play out in real time above your head. This complex dance of day and night, combined with Mercury's extreme orbital path, creates regions on the planet where the sun never rises at all. Near Mercury's poles, there are deep craters where the sun's rays never penetrate, creating permanently shadowed regions that remain colder than the surface of Pluto. In these eternal shadows, scientists have discovered something remarkable: deposits of water ice. Yes, water ice on Mercury, the planet closest to the sun. It seems almost paradoxical, but these polar shadows are so cold and so permanent that water ice can exist there indefinitely, preserved like frozen time capsules from the early solar system. These ice deposits might have been delivered by comets or formed from hydrogen in the solar wind, combining with oxygen in Mercury's rocks. Either way, they represent an oasis of the familiar in a world of extremes. The discovery of ice on Mercury reminds us that even in the most unlikely places, the building blocks of life can persist. It's a humbling thought that on a world where lead would melt during the day, there are regions where water ice has remained frozen for potentially billions of years, waiting in the darkness like a secret whispered by the early solar system. Mercury's rapid orbit also makes it a challenging target for spacecraft. To reach Mercury, a probe must not only travel toward the sun, but also slow down enough to match Mercury's orbital speed. This requires a complex series of gravitational assists, using the gravity of Venus and Mercury itself to gradually reduce the spacecraft's speed. It's like trying to catch a speeding train by jumping from a series of moving platforms, each one bringing you closer to the right speed and direction. Only 2 spacecraft have ever visited Mercury: Mariner 10 in the 1970s and Messenger, which orbited the planet from 2011 to 2015. Messenger's mission revealed Mercury to be far more complex and interesting than anyone had imagined. The planet has a surprisingly large iron core, making up about 75% of its radius, compared to Earth's core, which is only about 50% of our planet's radius. This oversized core suggests that Mercury might have formed much larger than it is today, perhaps losing much of its rocky mantle in a catastrophic impact early in the solar system's history. Or perhaps the intense solar radiation stripped away the lighter elements, leaving behind a world that's essentially a giant iron ball with a thin rocky shell. Either way, Mercury's composition tells a story of violence and extremes that matches its current harsh existence. The spacecraft also discovered that Mercury has a magnetic field, though much weaker than Earth's. This was surprising because Mercury rotates so slowly that scientists didn't expect it to generate the kind of dynamo effect that creates planetary magnetic fields. The discovery suggests that Mercury's core is still partially molten, still churning and generating magnetic fields despite the planet's small size and slow rotation. This magnetic field, weak as it is, interacts with the solar wind to create Mercury's thin atmosphere or exosphere. Atoms of sodium, potassium, and other elements are knocked off the surface by solar radiation and micrometeorite impacts, creating a tenuous envelope around the planet. This atmosphere is so thin that it's more like a controlled vacuum than the air we know, but it's enough to give Mercury spectacular auroras at its poles. Sheets of light dancing in the thin air as charged particles from the solar wind interact with the planet's magnetic field. As Mercury races through its orbit, it also serves as a natural laboratory for studying the effects of intense solar radiation. The planet receives about 7 times more solar energy per square meter than Earth does. This intense radiation pressure actually affects Mercury's orbit slightly, contributing to the precession that helped confirm Einstein's theory of relativity. The radiation pressure from sunlight might seem negligible, but over millions of years it adds up. It's like the gentle but persistent pressure of water against a dam, small in any given moment, but capable of profound effects over time. This radiation pressure, combined with the gravitational effects of relativity, makes Mercury's orbit one of the most precisely predictable in the solar system, a cosmic timepiece that helps us test our understanding of fundamental physics. Mercury's motion also affects its relationship with Earth in interesting ways. Because Mercury orbits the Sun faster than Earth does, it regularly laps us, creating what astronomers call synodic periods. About every 116 days, Mercury returns to the same position relative to Earth and the Sun, creating a cycle of appearances as a morning star, then an evening star, then disappearing behind the Sun before reappearing on the other side. Ancient astronomers noticed these cycles and used them to create some of the first accurate calendars. The Maya, in particular, were expert observers of Mercury's motions, incorporating its cycles into their complex calendar systems. They understood that Mercury's appearances followed predictable patterns, even if they didn't know the physical reasons behind those patterns. From Earth, Mercury never strays far from the Sun in our sky, never appearing more than about 28 degrees away from our star. This means it's only visible during twilight, either just before sunrise or just after sunset when the Sun is below the horizon, but Mercury is still above it. For most people, Mercury remains an elusive sight, a bright star-like point of light that appears briefly in the dawn or dusk sky before disappearing again. But for those patient enough to look for it, Mercury offers a special kind of beauty. It's a reminder of the clockwork precision of our solar system, a wandering star that has kept perfect time for billions of years. When you see Mercury in the sky, you're seeing a world in constant motion, racing around the Sun at speeds that would make our fastest jets seem like they're standing still. This motion, this wild ride around the Sun, has made Mercury a teacher as much as a neighbor. It taught us that our understanding of gravity was incomplete, leading to one of the greatest scientific revolutions in history. It taught us that worlds can exist in conditions so extreme they challenge our imagination, yet still harbor surprises like polar ice deposits. It taught us that even the smallest members of our solar system can have complex magnetic fields, thin atmospheres, and geological histories as rich as any larger world. Mercury's story is also a reminder of the delicate balance that makes Earth so special. Our planet orbits at just the right distance from the Sun to maintain liquid water on its surface, with just the right rotation rate to moderate temperatures between day and night. We have a substantial atmosphere that protects us from radiation and distributes heat around the globe. We have a strong magnetic field that shields us from harmful solar particles. Mercury, by contrast, shows us what happens when those conditions don't align. It's a world of extremes, where the difference between day and night is measured in hundreds of degrees, where the Sun dominates the sky like an angry god, where the very rocks would glow red hot at noon and become brittle with cold at midnight. It's beautiful in its harshness, but it's also a reminder of how fortunate we are to live in Earth's more temperate embrace. Yet there's something almost poetic about Mercury's existence, something that speaks to the deeper rhythms of the cosmos. Here is a world that has been racing around the Sun for over 4 billion years, never tiring, never slowing, following the same elliptical path with mathematical precision. It's been keeping time since before life appeared on Earth, a cosmic metronome marking the beats of solar system history. Every 88 days, Mercury completes another lap, another circuit of its endless race. In the time it takes you to watch a season change on Earth, Mercury experiences an entire year. In the time it takes a human to live a full life, Mercury completes nearly 300 orbits, each one identical to the last, each one a testament to the fundamental forces that govern our universe. As you drift towards sleep tonight, perhaps you'll think of Mercury out there in the darkness, racing through space at 35 miles per second, its day side glowing like a forge, while its night side freezes in the cosmic cold. Perhaps you'll imagine standing on its surface during one of those strange sunrises when the sun stops and reverses direction, a reminder that the universe is full of phenomena that challenge our earthbound intuitions. Or perhaps you'll simply appreciate the fact that we live in a universe where such precise, predictable motions are possible, where a small, rocky world can race around our star for billions of years without missing a beat, where the mathematics of orbital mechanics can be so elegant that they reveal the very nature of space and time itself. Mercury's wild ride around the sun continues tonight, tomorrow, and for billions of years to come. It's a dance that began when our solar system was young and will continue long after Earth's continents have shifted into unrecognizable shapes. In its motion, we see the deep rhythms of the cosmos, the patient persistence of gravity, and the beautiful precision of the laws that govern all celestial motion. And perhaps that's the most soothing thought of all, that in a universe of constant change, some things remain wonderfully, reliably constant. Mercury will be there tomorrow, racing through its orbit, keeping cosmic time, reminding us that even in the vast wilderness of space, there are patterns we can understand, motions we can predict, and an underlying order that connects the smallest planetary wanderer to the largest questions about the nature of reality itself. So rest well, fellow cosmic traveler, knowing that Mercury is out there, swift and solitary, riding its endless ellipse against the star-filled sky, carrying with it the secrets of gravity, time, and the wild beauty of worlds in motion. Now, Mercury is a planet that refuses to sit still. While we've explored its complex orbital dance and scorching surface conditions, there's something even more remarkable happening beneath that sun-baked exterior. Mercury is moving, constantly spinning and tumbling through space in ways that would make even the most experienced cosmic choreographer dizzy. You see, most planets in our solar system follow what we might call polite rotational behavior. Earth spins once every 24 hours, giving us our familiar day and night cycle. Mars does something similar, with a day lasting about 24.5 hours. Venus is a bit of a rebel, spinning backwards and taking 243 Earth days to complete one rotation. But Mercury? Mercury has decided to do something altogether different, something that baffled astronomers for decades. For the longest time, scientists believed Mercury was tidally locked to the sun, meaning one side always faced our star while the other remained in perpetual darkness. This would have made Mercury a planet of extremes, with one hemisphere eternally scorched and the other frozen solid. It seemed logical, given how close Mercury orbits to the sun. The sun's gravitational pull is so strong that it should have locked Mercury's rotation long ago, the way our moon is locked to Earth, always showing us the same face. But in 1965, radio astronomers made a discovery that turned this assumption upside down. Using the newly constructed Arecibo radio telescope in Puerto Rico, they bounced radio waves off Mercury's surface and measured how long it took for the signals to return. What they found was unexpected. The radio echoes revealed that Mercury was indeed rotating, but not in the way anyone had predicted. Mercury spins on its axis once every 58.6 Earth days. Now, that might not sound particularly unusual until you remember that Mercury's year, its orbital period around the sun, lasts 88 Earth days. This creates a very specific and very strange relationship. Mercury rotates exactly 3 times for every 2 orbits it makes around the sun. This is called a 3-to-2 spin-orbit resonance, and it's one of the most elegant examples of celestial mechanics in our solar system. Let me paint you a picture of what this means for someone standing on Mercury's surface, assuming you could survive the experience. If you were to plant a flag at noon on Mercury, when the sun is directly overhead, you would have to wait not one Mercury day, but 2 full Mercury years before the sun returned to that exact same position in the sky. That's 176 Earth days for a single solar day on Mercury. The sun would rise, crawl across the sky at a pace that would make a snail seem speedy, set, and then you'd have to wait through nearly an entire Earth year before seeing another sunrise from that same spot. But the story gets even stranger. Because of Mercury's highly elliptical orbit and this unusual rotation, the sun doesn't simply rise and set. Sometimes, from certain locations on Mercury, the sun actually appears to reverse direction in the sky. Imagine watching the sunrise, seeing the sun climb higher and higher, and then suddenly it stops, moves backward, and sets again in the same direction it rose. A few Earth days later, it rises again from the same place and finally continues its journey across the sky. This celestial magic trick happens because Mercury's orbital speed changes dramatically as it swings around its elliptical path, sometimes moving faster than its rotation can keep up with. This 3-to-2 resonance didn't happen by accident. It's the result of a delicate gravitational tug-of-war between Mercury and the Sun that played out over millions of years. When Mercury first formed, it likely rotated much faster, perhaps completing a day in just a few hours like many planets do when they're young. But the Sun's gravity gradually slowed Mercury's rotation through tidal forces, the same forces that cause ocean tides on Earth. Now, you might wonder why Mercury didn't become completely tidally locked like our moon. The answer lies in Mercury's elliptical orbit and its slightly non-spherical shape. Mercury is ever so slightly egg-shaped, and this symmetry created a gravitational handhold for the Sun to grab onto. As Mercury swings around its elliptical orbit, the changing distance from the Sun causes varying gravitational forces. These variations nudged Mercury into this 3-to-2 resonance, where the planet's rotation became synchronized with its orbital motion in this elegant mathematical relationship. The 3-to-2 resonance is actually more stable than complete tidal locking for Mercury's particular situation. If Mercury were perfectly round and on a perfectly circular orbit, it might indeed be tidally locked. But Mercury's elliptical orbit and slight asymmetry make the 3-to-2 resonance the most stable configuration. It's like a ball settling into the deepest groove on a tilted surface. This discovery revolutionized our understanding of how planets evolve. It showed us that tidal locking isn't inevitable, even for planets very close to their stars. Instead, planets can settle into these complex resonant relationships where rotation and orbit become locked in mathematical harmony. This has implications far beyond our solar system. When we discover exoplanets orbiting close to their stars, we now know they might not be simply tidally locked. They could be dancing to their own resonant rhythms. Mercury's rotation also affects its magnetic field. Though that field is much weaker than Earth's, the planet generates a magnetic field about 1% the strength of Earth's, created by the motion of liquid iron in Mercury's large core. This rotation-driven magnetic field interacts with the solar wind, creating a thin magnetosphere that provides minimal protection from the sun's radiation. The 3-to-2 resonance means this magnetic field is constantly changing orientation relative to the sun, creating complex interactions that we're still studying. The resonance also has implications for Mercury's surface features. The uneven heating caused by the planet's strange day-night cycle creates thermal stresses that crack and fracture the surface. These temperature changes happen slowly by Earth standards, but they're dramatic. Rocks expand and contract, creating the wrinkled terrain we see in spacecraft images. The planet's surface literally wrinkles like a raisin as it heats and cools over its long solar days. Understanding Mercury's rotation required patient observation and clever detective work. Before the radio telescope measurements, astronomers tried to determine Mercury's rotation by studying surface features through telescopes. But Mercury is small, close to the sun, and difficult to observe from Earth. The breakthrough came when scientists realized they could use Mercury as a cosmic mirror, bouncing radio waves off its surface and measuring the Doppler shift of the reflected signals. This technique revealed not just that Mercury was rotating, but exactly how fast and in what direction. The 3-to-2 resonance is just one example of how our solar system is full of these hidden mathematical relationships. Jupiter's moons dance in resonant chains, Saturn's rings are sculpted by resonant gaps, and even Pluto and Neptune are locked in a resonant embrace. These relationships emerge naturally from the gravitational interactions between objects in space, creating a cosmic symphony where everything moves in mathematical harmony. Mercury's unusual rotation also means that different parts of the planet experience dramatically different amounts of solar heating over time. Some regions spend more time facing the sun than others, creating hot spots and cold spots that persist for Mercury years. These temperature variations drive atmospheric circulation in Mercury's thin atmosphere and may influence how ice deposits accumulate in the planet's polar craters. The discovery of Mercury's 3-to-2 resonance was one of the first confirmations that space-based measurements could reveal truths hidden from ground-based observation. It paved the way for the space age of planetary exploration, showing that we needed to get our instruments closer to the planets if we wanted to understand them fully. This lesson guided the design of future missions to Mercury, including NASA's Messenger spacecraft and the European-Japanese Bepi Colombo mission currently en route to the planet. So Mercury spins through space in its stately 3-to-2 waltz, a cosmic dancer that took us decades to understand. Its motion reminds us that the universe is full of unexpected rhythms and hidden relationships, mathematical harmonies playing out on scales of time and space that dwarf human experience. Every 58 days, Mercury completes another rotation, another step in its eternal dance with the sun, a dance that will continue long after the last human eye has closed and the last telescope has fallen silent. In this rotation, we see the universe's tendency toward order emerging from chaos, complex patterns arising from simple gravitational rules. Mercury's motion is both utterly alien to our earthbound experience and deeply familiar in its mathematical elegance. It's a reminder that we live in a universe where even the smallest planet can teach us profound lessons about motion, time, and the hidden choreography that governs the cosmic dance. Looking back at Mercury's remarkable journey around the sun, we find ourselves drawn deeper into the cosmic clockwork that governs our innermost planetary neighbor. We've explored its rapid dance, its peculiar resonances, and its extreme conditions, but now it's time to venture into Mercury's hidden depths and uncover the treasures that lie beneath its sun-baked surface. Mercury is not just a world of extremes on its surface. It's a planet with secrets buried deep within its core, mysteries that have taken decades of careful observation and daring space missions to begin unraveling. What we've discovered challenges our assumptions about small planets and reveals a world far more dynamic and intriguing than its modest size might suggest. At the heart of Mercury lies one of the solar system's most disproportionate features, an enormous iron core that takes up roughly 75% of the planet's radius. To put this in perspective, imagine an apple where the core takes up 3/4 of the entire fruit. Earth's core, by comparison, occupies only about 55% of our planet's radius. This makes Mercury's core, relative to its size, the largest of any planet in our solar system. This oversized metallic heart gives Mercury a bulk density second only to Earth's, despite being less than 40% of Earth's size. It's as if someone compressed a much larger planet into a smaller package, keeping most of the heavy stuff and discarding the lighter materials. The result is a world that packs surprising gravitational punch for its size, with a surface gravity about 38% that of Earth's. But Mercury's iron core isn't just remarkably large, it's also partially molten, a discovery that came as a genuine surprise to planetary scientists. For decades, researchers assumed that such a small planet would have cooled completely long ago, its core frozen solid like a cosmic ice cube made of metal. Small objects lose heat faster than large ones after all, following the same principles that explain why a cup of coffee cools more quickly than a pot of soup. The evidence for Mercury's liquid core came from careful measurements of the planet's spin. Like a raw egg versus a hard-boiled one, a planet with a liquid interior wobbles differently when it rotates than one that's solid throughout. Earth-based radar observations detected tiny variations in Mercury's rotation, subtle wobbles that could only be explained by the sloshing of liquid metal deep within the planet's interior. This discovery raised an immediate question: how does Mercury maintain a partially molten core after 4.5 billion years? The answer likely lies in a combination of factors. The planet's eccentric orbit subjects it to varying gravitational stresses as it swings closer to and farther from the Sun, creating tidal heating that helps keep the interior warm. Additionally, Mercury's core likely contains sulfur and other elements that lower the melting point of iron, much like salt lowers the freezing point of ice on winter roads. The molten portions of Mercury's core have another remarkable consequence. They generate a magnetic field. Though much weaker than Earth's, about 1% the strength, Mercury's magnetic field was another surprise discovery. Most planetary scientists expected that such a small planet with its presumed solid core would have no magnetic field at all. Mercury's magnetic field is generated by the same dynamo process that creates Earth's magnetic field, the motion of electrically conducting liquid metal in the planet's core. As the molten iron flows and convects, it creates electric currents which in turn generate magnetic fields. It's a cosmic generator, powered by the planet's internal heat and rotation. This magnetic field, though weak, has profound implications for Mercury's interaction with the solar wind, the stream of charged particles flowing from the Sun. The field creates a magnetosphere, a protective bubble around the planet that deflects some of the solar wind's energy. However, Mercury's magnetosphere is far less robust than Earth's, allowing much more solar radiation to reach the planet's surface. The interaction between Mercury's magnetic field and the intense solar wind creates some of the most dynamic space weather in the inner solar system. Magnetic storms rage in Mercury's magnetosphere, and charged particles rain down onto the planet's poles, creating auroras that would be invisible to human eyes, but shine brightly in X-ray wavelengths. These magnetic interactions also contribute to Mercury's thin atmosphere, or more precisely, its exosphere, an incredibly tenuous envelope of atoms that barely qualifies as an atmosphere at all. Mercury's exosphere contains oxygen, sodium, hydrogen, helium, and potassium, all present in such minute quantities that the entire atmosphere would weigh less than a small car. The atoms in Mercury's exosphere come from several sources. Some are knocked off the surface by micrometeorite impacts, tiny space rocks that constantly bombard the planet. Others are sputtered away by the solar wind itself, as high-energy particles strike the surface and kick atoms into space. Still others are released when volatile materials in the surface rocks are heated by the sun's intense radiation. Sodium is particularly prominent in Mercury's exosphere, creating a glowing tail that extends millions of kilometers into space, visible to specialized telescopes on Earth. This sodium tail, pushed by solar radiation pressure, streams away from the sun like a cosmic windsock, providing astronomers with a real-time indicator of the conditions in Mercury's immediate environment. But perhaps Mercury's most surprising secret lies hidden in its polar regions, in craters that never see sunlight. Despite being the closest planet to the sun, despite experiencing temperatures that can melt lead, Mercury harbors water ice at its poles. This discovery seemed almost absurd when first proposed. How could ice exist on a world where noon temperatures soar above 800 degrees Fahrenheit? The answer lies in the peculiar geometry of Mercury's orbit and rotation. Because Mercury's rotational axis is nearly perpendicular to its orbital plane, it has virtually no axial tilt. The floors of deep craters at the poles exist in permanent shadow, never receiving direct sunlight. In these shadowed regions, temperatures plummet to -300 degrees Fahrenheit or lower, cold enough to preserve water ice for billions of years. Radar observations from Earth first hinted at these deposits, showing bright reflections from Mercury's polar regions that look suspiciously like ice. The Messenger spacecraft later confirmed the discovery, mapping extensive deposits of water ice mixed with darker organic compounds. The water ice likely arrived via comet impacts over Mercury's long history. Comets, those dirty snowballs from the outer solar system, occasionally crash into the inner planets, delivering water and organic materials. On Mercury, most of this water would immediately vaporize and escape to space, but some would find its way to the permanently shadowed polar regions, where it could freeze and accumulate over geological time. These ice deposits represent a fascinating paradox. The solar system's hottest planet is also home to some of its most pristine and ancient ice. The organic compounds mixed with the ice, likely complex carbon-based molecules delivered by the same comets, add another layer of intrigue. While Mercury is far too hostile to harbor life as we know it, these deposits provide a record of the organic chemistry that has been delivered throughout the inner solar system's history. The story of Mercury's interior extends beyond its core to its thin, rocky mantle and heavily cratered crust. The planet's surface bears the scars of 4 billion years of bombardment, a museum of the early solar system's violent youth. Unlike Earth, where plate tectonics constantly resurfaces the planet and weather erodes ancient features, Mercury has preserved its primordial face. The largest of Mercury's impact basins, the Caloris Basin, stretches nearly 1,000 miles across, roughly the distance from New York to Florida. This enormous crater was carved by an asteroid impact so powerful that it sent shockwaves completely around the planet, creating a jumbled, hilly terrain on the exact opposite side of Mercury from the impact site. Mercury's surface also reveals evidence of the planet's thermal history in the form of scarps, long, curved cliffs that snake across the landscape for hundreds of miles. These scarps formed as Mercury's interior cooled and contracted, causing the planet's crust to wrinkle like the skin of a drying apple. The planet has literally shrunk over its lifetime, its radius decreasing by several miles as its interior lost heat to space. The composition of Mercury's crust tells another story of extremes. The planet's rocks are unusually rich in sulfur and poor in iron compared to other terrestrial planets, suggesting that Mercury formed under unique conditions in the early solar system. Some theories propose that Mercury was once much larger, but a giant impact stripped away most of its rocky mantle, leaving behind the metal-rich world we see today. Another hypothesis suggests that Mercury formed in a region of the solar nebula where temperatures were so high that only the most refractory materials, those with the highest melting points, could condense into solid form. This would explain both the planet's high metal content and its unusual surface chemistry. As we peer deeper into Mercury's mysteries, we find a world that defies simple categorization. It's simultaneously the most extreme and the most subtle of planets, a world of blazing heat and hidden ice, of ancient craters and active geology, of powerful magnetic fields generated by the smallest of cores. Mercury reminds us that in astronomy, size doesn't always determine significance. This modest world, barely larger than Earth's moon, has taught us profound lessons about planetary formation, magnetic field generation, space weathering, and the delivery of water and organic compounds throughout the solar system. The planet's story is far from complete. Future missions may walk on Mercury's surface, drill into its ice deposits, and probe the mysteries of its oversized core. Each new discovery adds another chapter to the remarkable tale of the solar system's innermost world, a planet that has spent billions of years keeping its secrets while dancing its eternal, precise waltz around our sun. In Mercury's hidden depths, we find not just iron and rock, but the keys to understanding how planets form, evolve, and sometimes defy our expectations. It's a world that proves that even in the most familiar of neighborhoods, our own solar system, there are still wonders waiting to be discovered, still stories waiting to be told. Mercury, that little gray world closest to our sun, is far more fascinating than its modest appearance suggests. We've traced its wild 88-day sprint around our star, marveled at its peculiar 3-2 dance of rotation, and discovered water ice hiding in the permanent shadows of its poles. We've learned about its enormous iron heart, its magnetic field interactions with the solar wind, and the way its heavily cratered surface tells the story of billions of years of cosmic bombardment. But there's one more chapter to Mercury's story that we haven't fully explored yet, and it might just be the most intriguing of all. You see, Mercury isn't just a world of extremes in temperature, rotation, and orbital mechanics. It's also a world that has taught us something profound about the nature of space and time itself. Albert Einstein, when he proposed his theory of general relativity in 1915, knew he needed to test it against the real universe. His equations predicted that massive objects would warp space-time, and that this warping would affect the motion of everything around them, including the orbits of planets. But how do you test such a thing? How do you measure the curvature of space itself? The answer came from Mercury's orbit, and specifically from a tiny discrepancy that had been puzzling astronomers for decades. You see, Mercury's orbit doesn't quite behave the way Newton's laws of gravity predict it should. It's close, mind you, remarkably close, but there's a small deviation, a gentle drift that accumulates over time. Mercury's orbit is elliptical, like all planetary orbits, and the point where it comes closest to the Sun is called perihelion. According to Newton's laws, accounting for the gravitational pull of all the other planets, Mercury's perihelion should shift by about 525 arcseconds per century. An arcsecond, just to give you a sense of scale, is 1/3600th of a degree. It's the apparent size of a coin, viewed from about 4 kilometers away. Incredibly tiny. But when astronomers measured Mercury's actual orbital precession, they found something unexpected. The perihelion was shifting by about 568 arcseconds per century. That's a difference of only 43 arcseconds, less than 2/100ths of a degree per century. It sounds almost negligible, doesn't it? But in the precise world of celestial mechanics, it was a glaring mystery. For decades, astronomers tried to explain this discrepancy. Perhaps there was an undiscovered planet between Mercury and the Sun tugging on Mercury's orbit. They even gave this hypothetical world a name: Vulcan. Search parties scanned the sky looking for this elusive inner planet during solar eclipses when its faint light might be visible against the Sun's corona. But Vulcan was never found, because Vulcan didn't exist. The real answer was far more elegant and revolutionary. Einstein's general relativity predicted that the Sun's immense mass would warp the fabric of space-time around it, and that this warping would cause Mercury's orbit to precess by exactly 43 arcseconds per century. When Einstein calculated this value and found it matched the observed discrepancy perfectly, he later wrote that he had heart palpitations. The theory worked. Space and time were indeed curved by mass and energy. This was one of the first great confirmations of general relativity, and it came from Mercury, the smallest planet in our solar system. That tiny world, racing around the Sun in its eccentric orbit, was actually tracing the curvature of space-time itself. Every orbit was a testament to Einstein's revolutionary understanding of gravity, not as a force, but as geometry. But Mercury's role as a cosmic laboratory didn't end there. The little planet continues to serve as a testing ground for our understanding of physics. Modern measurements of Mercury's orbit, made possible by radar ranging and spacecraft observations, have allowed scientists to test relativity to extraordinary precision. They can now measure the perihelion advance to within a few thousandths of an arcsecond per century, and Einstein's theory continues to pass every test. Mercury has also helped us understand other relativistic effects. Time dilation, the phenomenon where time runs slower in stronger gravitational fields, affects Mercury's motion in measurable ways. The planet's proximity to the Sun means it experiences stronger gravity than Earth does, and this causes time to run slightly slower there compared to our reference frame. It's a tiny effect, but it's real and measurable. There's also the relativistic correction to Mercury's kinetic energy. The planet moves so fast in its orbit, especially at perihelion where it reaches 47 kilometers per second, that relativistic effects become noticeable. At these speeds, Mercury's mass effectively increases slightly, and this too affects its orbital motion in ways that general relativity predicts perfectly. Perhaps most fascinatingly, Mercury helps us probe the very nature of the gravitational constant itself. Scientists have used precise measurements of Mercury's orbit to test whether the strength of gravity might be changing over cosmic time. So far, these tests suggest that gravity has remained constant, at least over the timescales we can measure. All of this makes Mercury not just a planet, but a natural experiment in fundamental physics. Every time it completes an orbit, every time it swings around the Sun and feels the full force of our star's gravitational embrace, it's providing data about the deepest laws of nature. It's remarkable to think that this small, seemingly unremarkable world has played such a crucial role in our understanding of the universe. And Mercury's scientific story is far from over. Future missions may help us probe even more exotic predictions of relativity and other theories of gravity. Some scientists have proposed testing whether Mercury's orbit shows signs of extra dimensions, or whether it might reveal new physics beyond Einstein's theory. The little planet that once puzzled astronomers with its stubborn refusal to follow Newton's laws exactly continues to be our guide into the deepest mysteries of space, time, and gravity. So the next time you glimpse Mercury in the twilight sky, that faint dot of light dancing near the horizon, remember that you're looking at one of science's greatest teachers. In its eccentric orbit, in its rapid motion, in its precise dance around the Sun, Mercury carries the signature of curved space-time itself. It's a small world with an enormous story, a testament to the beautiful relationship between observation and theory, between the cosmic and the quantum, between the dance of planets and the deepest truths about reality itself. We've journeyed through the cosmic furnace of stellar formation, watched Mercury's intricate dance with the Sun, and witnessed the birth of magnetic fields that shield worlds from solar fury. Now, as we drift deeper into Mercury's story, we encounter one of the most remarkable discoveries in planetary science: the presence of water ice on the hottest planet in our solar system. Picture this paradox for a moment. Mercury, locked in its eternal waltz with the Sun, receives 7 times more solar energy than Earth. Its dayside temperatures soar to over 400 degrees Celsius, hot enough to melt lead. And yet hidden in the permanent shadows of its polar craters lies something that shouldn't exist there at all: water ice. Billions of tons of it, quietly preserved in the darkness like cosmic time capsules from the early solar system. This discovery fundamentally changed how we think about Mercury. For decades, scientists assumed that any water on the innermost planet would have been vaporized and stripped away eons ago. The solar wind, that relentless stream of charged particles flowing from the Sun, should have scoured Mercury's surface clean of anything as delicate as water molecules. But nature, as always, found a way to surprise us. The story begins with Mercury's unusual relationship with sunlight. Unlike Earth, which spins on a tilted axis, giving us seasons, Mercury's rotational axis is nearly perpendicular to its orbital plane. This means the sun never rises very high in Mercury's polar skies. At the poles themselves, the sun skims along the horizon, never climbing more than a few degrees above it. This creates something extraordinary: regions of permanent shadow. Deep within certain polar craters, areas exist where sunlight has never touched the surface. These are among the coldest places in the solar system, with temperatures plunging to -200 degrees Celsius. In these frigid sanctuaries, water ice can exist for billions of years, protected from the sun's destructive heat by nothing more than topography and shadow. The evidence for this water ice came from multiple sources, each adding another piece to the puzzle. First, Earth-based radar observations in the 1990s detected highly reflective patches at Mercury's poles. The radar signatures were consistent with water ice, but scientists remained cautious. Could these bright spots be something else entirely? Perhaps deposits of sulfur or some other reflective material? The answer came from NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger's instruments painted a detailed picture of Mercury's polar regions. Its neutron spectrometer detected hydrogen signatures consistent with water ice, while its laser altimeter mapped the topography of polar craters with unprecedented precision. The data revealed that the radar-bright regions perfectly matched areas of permanent shadow within these craters. But Messenger discovered something even more intriguing. The ice deposits weren't uniform. Some appeared to be relatively pure water ice, while others seemed to be buried beneath a dark layer of organic material. This organic layer, rich in carbon compounds, likely arrived on Mercury the same way the water did, through impacts from comets and asteroids. Think about the implications of this discovery. Every drop of water ice on Mercury represents a fragment of the early solar system, a piece of the primordial materials from which the planets formed. Comets, sometimes called dirty snowballs, are repositories of water and organic compounds that formed in the outer reaches of the solar system. When these ancient wanderers venture close to the sun, some inevitably collide with planets, delivering their cargo of water and carbon-based molecules. On Earth, this process may have been crucial for the development of life. The water in our oceans, the carbon in our bodies, may have arrived through similar cosmic deliveries. Mercury's ice deposits offer us a pristine sample of these ancient materials, preserved in a deep freeze for billions of years. The discovery also reveals something profound about planetary environments. We tend to think of habitability in simple terms. A planet is either too hot or too cold, too close to its star or too far away. But Mercury shows us that even in the most extreme environments, pockets of moderation can exist. While Mercury's equatorial regions are furnaces hot enough to melt metal, its polar regions harbor ice colder than Antarctica. This concept of environmental niches has important implications for astrobiology. If water ice can survive on Mercury, what other surprises might await us on seemingly inhospitable worlds? The icy moons of Jupiter and Saturn, once thought too cold for life, are now known to harbor subsurface oceans. Mars, despite its thin atmosphere and frigid temperatures, shows evidence of past and possibly present liquid water. Mercury's water ice also tells us something about the planet's history. The ice deposits are relatively fresh in geological terms, suggesting that impacts continue to deliver water to Mercury even today. This ongoing process means that Mercury's polar regions are dynamic environments, constantly being resupplied with new materials from space. The organic compounds found mixed with the ice add another layer to this story. On Earth, organic molecules are the building blocks of life. While we shouldn't expect to find life in Mercury's polar craters, the presence of these compounds shows that the basic chemistry of life can survive even in extreme environments. These organic materials, shielded from the sun's harsh radiation by the ice and the crater walls, represent a chemical library that scientists are eager to study. Future missions to Mercury will undoubtedly focus on these polar deposits. The European Space Agency's Bepi-Colombo mission, currently en route to Mercury, will study the planet's polar regions in unprecedented detail. Scientists hope to determine the exact composition of the ice, map its distribution, and understand how it interacts with Mercury's tenuous atmosphere. There's also the tantalizing possibility of human exploration. While Mercury's day side is far too hot for conventional spacecraft, the polar regions might be accessible. The combination of water, ice, and organic compounds could potentially support future robotic missions or even serve as resources for human exploration of the inner solar system. As we contemplate Mercury's hidden ice, we're reminded that the universe is full of contradictions and surprises. The hottest planet harbors some of the coldest places in the solar system. The most sun-scorched world preserves ancient water in perpetual darkness. These paradoxes challenge our assumptions and expand our understanding of what's possible in planetary science. Mercury's water ice is more than just a scientific curiosity. It's a bridge between the ancient past and the dynamic present, between the cosmic processes that shaped our solar system and the ongoing evolution of planetary environments. In those dark, cold craters, we glimpse the raw materials from which worlds are made, and perhaps even the conditions under which life might arise. The next time you see Mercury in the evening or morning sky, that bright dot racing across the twilight, remember that it carries within it both fire and ice, both the fury of stellar radiation and the gentle preservation of primordial water. It's a reminder that even in the most extreme environments, nature finds ways to create islands of stability, pockets of the unexpected, and reservoirs of the precious materials that make worlds like ours possible. So the next time you see Mercury in the evening sky, that tiny wandering star catching the last rays of sunlight, remember you're looking at a world of extremes, a planet where the sun looms 3 times larger than it does from Earth, where temperatures could melt lead on one side, while water ice hides in eternal shadows on the other. A place where a single day lasts longer than 2 of its years, where the surface bears the scars of billions of years of cosmic bombardment, and where a massive iron heart generates a magnetic field against all odds. Mercury may be small, but it carries outsized scientific importance. Its precise orbit helped confirm Einstein's theory of general relativity, proving that space and time themselves can bend and warp. Its surface tells the story of the early solar system, a time when planets were still forming and the inner system was a chaotic shooting gallery of debris. Its surprising magnetic field and hidden water ice remind us that even the most extreme worlds can hold secrets that challenge our assumptions. The missions that have visited Mercury, from Mariner 10's first glimpse to Messenger's comprehensive survey and Bepi-Colombo's ongoing investigation, have transformed our understanding of this enigmatic world. We've learned that Mercury is not just a dead rock baking in the sun, but a dynamic planet with its own unique geology, a complex relationship with the solar wind, and an interior structure unlike any other planet we know. Perhaps most remarkably, Mercury has taught us about resilience. Despite being blasted by solar radiation, despite losing most of its atmosphere to space, despite enduring temperature swings that would shatter most materials, Mercury endures. It continues its eternal dance around the sun, completing orbit after orbit with clockwork precision, a testament to the fundamental forces that govern our cosmos. The study of Mercury also reminds us how much we still don't know. Why did it form with such a large iron core? How did water ice survive in a world so close to the sun? What processes shaped its unique surface features? Each answer we discover leads to new questions, new mysteries to unravel. In many ways, Mercury represents the frontier spirit of planetary science. It's difficult to reach, challenging to study, and unforgiving to spacecraft that dare to venture into its neighborhood. Yet the scientific rewards have been immense. Every image returned, every measurement taken, Every orbital pass completed adds another piece to the puzzle of how our solar system formed and evolved. As we look toward the future, Mercury will continue to play a crucial role in our understanding of planetary science. Bepi Colombo's ongoing mission promises to reveal even more secrets, from the composition of its thin exosphere to the precise structure of its magnetic field. Future missions might one day land on its surface, drilling into the ancient terrain to read the geological record written in its rocks. But you don't need a spacecraft to appreciate Mercury's wonder. On any clear evening when the planet appears as a bright star low on the horizon, you can contemplate the remarkable world it represents. That tiny point of light is racing around the sun at nearly 50 kilometers per second, its surface alternately baking and freezing, its iron core slowly cooling after billions of years. Mercury's story is ultimately our story too. The same processes that shaped Mercury affected all the terrestrial planets, including Earth. The heavy bombardment that scarred Mercury's surface also pummeled our own world, possibly delivering the water and organic compounds that would later give rise to life. The solar wind that strips Mercury's atmosphere also interacts with Earth's magnetic field, creating the beautiful auroras that dance across our polar skies. In the grand symphony of the solar system, Mercury plays a unique and vital part. Its rapid orbit sets the tempo, its extreme environment tests the limits of planetary physics, and its ancient surface preserves the memory of our cosmic origins. Every 88 days, as Mercury completes another circuit of the Sun, it reminds us that our solar system is a place of endless motion, constant change, and infinite wonder. So tonight, as you drift towards sleep, perhaps you'll dream of that swift messenger racing through the cosmos, carrying secrets from the sun to the edge of space and back again. In the morning, Mercury will still be there, continuing its eternal journey, waiting for the next generation of explorers to unlock its remaining mysteries. The smallest planet in our solar system may be, but its impact on our understanding of the universe is immeasurably vast. Looking at Mercury's remarkable journey through space, we've witnessed its breakneck orbital dance, explored its peculiar relationship with time, and marveled at the resilience of ice in the most unlikely of places. We've followed the footsteps of robotic explorers and watched as Mercury confirmed Einstein's boldest predictions about the fabric of space-time itself. But there's still more to this enigmatic world that deserves our gentle attention before we drift towards sleep. Mercury's story is ultimately one of extremes, and perhaps nowhere is this more evident than in the planet's relationship with its own magnetic field. For such a small world, Mercury possesses a surprisingly robust magnetic field, roughly 1% the strength of Earth's. This might not sound impressive, but for a planet barely larger than our moon, it's quite remarkable. The magnetic field tells us something profound about Mercury's interior structure and the dynamic processes still churning away beneath its heavily cratered surface. The source of this magnetism lies deep within Mercury's oversized core. Unlike Earth, where the magnetic field is generated by the motion of liquid iron in the outer core, Mercury's situation is more complex and frankly more mysterious. The planet's core makes up about 3/4 of its radius, an unusually large proportion that speaks to Mercury's violent formation history. Within this massive iron core, convection currents still flow, driven by the gradual cooling and solidification of the planet's interior. These currents, combined with Mercury's slow rotation, create the dynamo effect responsible for the magnetic field. But Mercury's magnetism isn't just a curiosity for planetary scientists. It has real consequences for the planet's interaction with the solar wind, that constant stream of charged particles flowing outward from the sun. Earth's magnetic field creates a protective bubble called the magnetosphere, shielding us from most of this solar radiation. Mercury has its own magnetosphere, though it's much smaller and more dynamic than ours. The planet's proximity to the sun means it faces a solar wind roughly 10 times more intense than what Earth experiences. Mercury's magnetic field deflects some of this radiation, but not all of it. The result is a constantly shifting, pulsing magnetosphere that expands and contracts as the solar wind pressure varies. This magnetic drama has another consequence. It contributes to Mercury's extremely thin atmosphere, or exosphere as scientists prefer to call it. The interaction between the solar wind and Mercury's surface literally knocks atoms off the planet, creating a tenuous envelope of sodium, potassium, calcium, and other elements. This atmosphere is so thin that it's essentially a vacuum by Earth standards, but it's dynamic and ever-changing. The composition shifts depending on Mercury's position in its orbit, the intensity of the solar wind, and even the time of day. It's like watching the planet breathe, though very, very quietly. The study of Mercury's magnetosphere has revealed something else intriguing: magnetic tornadoes. These are twisted bundles of magnetic field lines that form when Mercury's magnetic field interacts with the solar wind. These structures can channel solar wind particles directly to Mercury's surface, contributing to the ongoing erosion of the planet and the replenishment of its thin atmosphere. It's a process that's been going on for billions of years, slowly but steadily altering the planet's surface composition and adding to the complexity of its already challenging environment. Temperature remains one of Mercury's most defining characteristics, and the extremes are truly staggering. During the day, surface temperatures can reach 427 degrees Celsius, hot enough to melt lead, zinc, and tin. But it's not just the peak temperatures that are remarkable, it's how quickly they change. Mercury's lack of a substantial atmosphere means there's nothing to moderate temperature swings. As the planet rotates and different regions move from blazing sunlight into shadow, temperatures can drop by hundreds of degrees within hours. It's like living on a world with the most extreme seasonal changes imaginable, except these seasons last for months and the temperature swings could kill you in minutes. The night side of Mercury tells a different story entirely. Temperatures plummet to minus 173 degrees Celsius, cold enough to freeze carbon dioxide and create conditions more hostile than the surface of Mars. This temperature differential between day and night creates thermal stresses that crack and fracture the planet's surface rocks. Over millions of years, this thermal cycling has contributed to the weathering of Mercury's landscape, breaking down rocks and contributing to the fine dust that covers much of the planet's surface. But perhaps the most poetic aspect of Mercury's temperature story is found at its poles. Here, in craters where the sun never shines, temperatures remain permanently below minus 200 degrees Celsius. These polar regions are some of the coldest places in the solar system, colder even than the surface of Pluto. And it's in these frigid shadows that water ice persists, a reminder that even the planet closest to the sun harbors frozen remnants of the solar system's formation. The presence of water ice at Mercury's poles raises fascinating questions about the delivery and preservation of volatiles throughout the solar system. This ice likely arrived via comets or asteroids billions of years ago, and it's been sitting there ever since, locked in permanent shadow. Some of these deposits may be mixed with organic compounds, carbon-based molecules that are the building blocks of life as we know it. While Mercury is far too extreme to harbor life itself, the discovery of organics there suggests that the ingredients for life may be more widely distributed throughout the solar system than we once thought. Mercury's surface features tell stories of a violent past and an active interior. The planet is covered with impact craters, evidence of the heavy bombardment that all the inner planets experienced during the solar system's youth. But Mercury also shows signs of more recent geological activity. The planet has shrunk over time as its interior has cooled, causing the surface to wrinkle and fold like the skin of a drying apple. These features, called lobate scarps, can stretch for hundreds of kilometers and rise several kilometers high. They're evidence that Mercury is still geologically active, though much less so than Earth. One of Mercury's most distinctive features is the Caloris Basin, a massive impact crater about 1,550 kilometers in diameter. This ancient scar was created when an asteroid or comet roughly 100 kilometers across slammed into Mercury billions of years ago. The impact was so violent that it sent shockwaves through the entire planet, creating a region of jumbled, hilly terrain on the exact opposite side of Mercury from the impact site. It's as if the planet rang like a bell, with the seismic waves focusing their energy at the antipodal point and scrambling the landscape there. The Caloris Basin also demonstrates Mercury's complex geological history. After the initial impact, the basin was partially filled with volcanic lava flows, creating smooth plains that contrast sharply with the heavily cratered terrain elsewhere on the planet. These volcanic deposits are evidence that Mercury was once much more geologically active than it is today, with molten rock reaching the surface and reshaping the landscape. Mercury's small size and proximity to the Sun have made it one of the most challenging planets to study. Until recently, much of what we knew about Mercury came from brief glimpses captured by the Mariner 10 spacecraft in the 1970s, which managed to photograph only about 45% of the planet's surface during 3 flyby encounters. It wasn't until the Messenger mission, which orbited Mercury from 2011 to 2015, that we got our first comprehensive look at this mysterious world. Messenger's discoveries revolutionized our understanding of Mercury. The spacecraft mapped the entire planet in detail, measured its magnetic field, analyzed its thin atmosphere, and confirmed the presence of water ice at the poles. Perhaps most importantly, Messenger revealed that Mercury is much more geologically complex than anyone had imagined. The planet shows evidence of past volcanic activity, tectonic processes, and ongoing interaction with the solar environment. The data from Messenger also helps solve one of Mercury's biggest mysteries. Why is it so dense? The answer lies in its formation history. Current theories suggest that Mercury may have formed closer to its current size, but then suffered a catastrophic impact that stripped away much of its rocky mantle, leaving behind a planet that's mostly iron core with just a thin shell of rock. Alternatively, the intense heat from the young sun may have vaporized and blown away much of Mercury's original rocky material. Either way, Mercury represents an extreme outcome of planetary formation, a world that has been sculpted by forces that would be unimaginable on our gentle Earth. Currently, Mercury is being visited by another ambitious mission, BepiColombo, a joint European-Japanese endeavor that launched in 2018 and will arrive at Mercury in 2022-2025. This mission consists of 2 spacecraft that will study Mercury from different perspectives, providing the most detailed examination of the planet ever attempted. BepiColombo will map Mercury's surface and interior structure, study its magnetic field and thin atmosphere, and search for additional evidence of water ice and organic compounds. What makes BepiColombo particularly exciting is its ability to study Mercury's relationship with the Sun in real time. The spacecraft will observe how the solar wind interacts with Mercury's magnetosphere, how the planet's thin atmosphere changes throughout its orbit, and how the extreme temperature variations affect the surface. It's like having a weather station and geological survey team combined, all studying the most extreme environment in the inner solar system. Mercury's story is ultimately a reminder of how diverse and dynamic our solar system truly is. Here's a world that experiences the most extreme temperature swings imaginable, harbors ancient water ice in permanent shadow, and maintains a surprisingly active magnetic field despite its small size. It's a planet that has been carved by impacts, shaped by thermal stress, and continuously modified by its intense relationship with the Sun. In many ways, Mercury represents the solar system's laboratory for extreme physics. The planet's environment tests the limits of what we know about planetary formation, magnetic field generation, and the preservation of volatiles in harsh conditions. Every measurement from Mercury helps us understand not just our own solar system, but the thousands of exoplanets we've discovered orbiting other stars, many of which likely experience conditions just as extreme as Mercury's. As we continue to study Mercury, we're reminded that even the smallest and most seemingly inhospitable worlds can hold profound secrets. This tiny planet, racing around the sun in its eternal dance, carries within its iron heart and ice-shadowed craters the story of our solar system's formation and evolution. It's a world of extremes that challenges our understanding and rewards our curiosity with insights that reach far beyond its small, sun-baked surface. So the next time you glimpse Mercury in the twilight sky, that faint wandering star hugging close to the horizon, remember that you're looking at one of the most remarkable worlds in our cosmic neighborhood. A planet where the sun appears to move backward in the sky, where ice exists in the shadows of the hottest place in the solar system, and where the very fabric of space-time is stretched and warped in ways that confirm our deepest theories about the nature of reality itself. Mercury may be small, but its story is vast, and we're only just beginning to read the chapters written in its ancient, crater-scarred surface. As we've journeyed through the cosmic dance of Mercury's formation, we arrive at a crucial chapter in planetary science, one that transforms our understanding of how worlds are born and shaped. The story of Mercury isn't just about one small planet hugging close to our sun. It's a window into the fundamental processes that sculpt every rocky world in our universe. When we look at Mercury today, with its enormous iron core comprising nearly 3/4 of its radius, we're witnessing the end result of a cosmic forge that operated under the most extreme conditions imaginable. This isn't simply a planet that formed and cooled. This is a world that was literally melted, stripped, and rebuilt by the relentless forces of the early solar system. The leading theory for Mercury's unusual composition tells a tale of cosmic violence that would make even the most dramatic science fiction seem tame. Picture the early solar system as it was 4.5 billion years ago, a chaotic nursery filled with planetary embryos, asteroid-sized building blocks, and clouds of dust and gas still swirling from the solar nebula's collapse. In this primordial shooting gallery, collisions weren't rare accidents, but the fundamental mechanism by which planets grew. Mercury likely began its existence as a much larger world, perhaps twice its current size, with a more typical ratio of rocky mantle to iron core. But its proximity to the young sun made it a target in a cosmic game of billiards that would reshape its very essence. The giant impact hypothesis suggests that early in Mercury's history, when the planet was still partially molten from the heat of formation, another planetary embryo, possibly Mars-sized, slammed into it with unimaginable force. The collision was so violent that it stripped away much of Mercury's rocky outer layers, blasting them into space where they either fell into the sun or were swept up by other growing planets. What remained was essentially the iron heart of the original world, now naked and exposed, with only a thin shell of rocky material clinging to its metallic core. This catastrophic reshaping explains why Mercury's core is proportionally larger than any other planet in our solar system. But the giant impact theory is just one piece of Mercury's formation story. Another process may have been equally important: the slow, patient work of solar winds and radiation pressure from our young sun. In its earliest days, the sun was more active and temperamental than it is today, producing powerful stellar winds that could literally blow away the lighter elements from nearby planets. Over millions of years, this cosmic sandblasting may have gradually eroded Mercury's outer layers, preferentially removing the lighter rocky materials while leaving the dense iron core behind. There's also the possibility that Mercury's strange composition results from where and how it formed in the solar disk. The inner regions of the early solar system were so hot that only the most refractory materials, those with the highest melting points, could condense from the solar nebula. Iron and nickel, being among these heat-resistant materials, would have been abundant near Mercury's current orbit, while lighter, more volatile compounds would have been vaporized and blown outward to cooler regions of the solar system. This process of thermal processing in the inner solar nebula might explain not just Mercury's iron-rich composition, but also its relative lack of lighter elements like sulfur and potassium. The planet we see today may be the natural result of formation in the hottest, most extreme environment in our solar system, a cosmic foundry where only the strongest materials could survive. Recent data from the Messenger mission has added fascinating new chapters to Mercury's formation story. The discovery of water ice in permanently shadowed polar craters tells us that even in this sun-scorched world, the materials needed for life as we know it can find refuge in the most unlikely places. These deposits likely arrived long after Mercury's formation, delivered by comets and asteroids that somehow managed to deposit their precious cargo in the few places on Mercury where the sun never shines. The presence of organic compounds alongside this water ice is perhaps even more intriguing. These carbon-based molecules, the building blocks of life, somehow survived in an environment that reaches temperatures hot enough to melt lead. Their existence suggests that the processes that deliver the ingredients for life operate even in the most extreme environments, and that the boundary between habitable and uninhabitable worlds may be more complex than we once thought. Mercury's geological features also tell stories of its violent past and dynamic present. The enormous Calorus Basin, stretching over 1,500 kilometers across, bears witness to one of the largest impact events in the inner solar system. The shock waves from this collision were so powerful that they traveled completely through the planet and created chaotic, jumbled terrain on the exact opposite side of Mercury, a phenomenon that demonstrates just how thoroughly impacts can reshape entire worlds. The planet's surface is also crisscrossed with scarps, massive cliffs that can stretch for hundreds of kilometers and tower several kilometers high. These features formed as Mercury's interior cooled and contracted, causing the planet's surface to wrinkle like a deflating balloon. The fact that these scarps cut across crater floors tells us that Mercury was still shrinking relatively recently in geological terms, perhaps within the last billion years. This ongoing contraction reveals something profound about Mercury's interior structure. The planet's large iron core is still cooling and solidifying, releasing heat that powers the weak but measurable magnetic field that Messenger detected. This magnetic field, though only about 1% as strong as Earth's, tells us that Mercury's core is at least partially liquid, a remarkable fact for such a small world that should have cooled completely long ago. The story of Mercury's formation has implications that extend far beyond our solar system. As we discover more and more exoplanets orbiting other stars, we're finding that Mercury-like worlds, small, dense, iron-rich planets orbiting close to their host stars, are surprisingly common. These discoveries suggest that the processes that shape Mercury may be fundamental aspects of planet formation, operating wherever rocky worlds form in the intense radiation environment close to their stars. Some of these exoplanets are even more extreme than Mercury, with surfaces hot enough to vaporize rock and atmospheres of metallic gases. Others orbit so close to their stars that they're tidally locked, with one side permanently facing their sun while the other remains in eternal darkness. These alien worlds help us understand that Mercury, for all its extremes, represents just one point on a vast spectrum of possible planetary outcomes. The formation of Mercury also illuminates the role of chaos and contingency in planetary evolution. Small changes in the timing of impacts, the composition of the solar nebula, or the early activity of the sun could have produced a very different world. Mercury might have retained more of its rocky mantle, developed a thicker atmosphere, or even been destroyed entirely in a collision that scattered its remains throughout the inner solar system. This sensitivity to initial conditions reminds us that the planets we see today are not inevitable outcomes, but rather the survivors of a cosmic lottery. Each world carries within its structure and composition the record of countless chance events, collisions avoided or endured, materials gathered or lost, thermal histories shaped by the precise dance of gravitational forces and stellar evolution. As we prepare to welcome Bepi Colombo to Mercury in the coming years, we stand on the threshold of even deeper revelations about this enigmatic world. This ambitious mission, with its suite of advanced instruments and its planned 7-year survey of Mercury's surface, interior, and environment, promises to answer questions we've carried since Mariner 10's first glimpse of the planet nearly 50 years ago. But perhaps the most profound lesson from Mercury's formation story is how it demonstrates the power of scientific inquiry to reveal the hidden histories written in stone and metal across the cosmos. Every crater, every cliff, every magnetic field measurement is a sentence in the autobiography of a world, waiting for us to learn the language needed to read its tale. In the end, Mercury stands as a testament to the resilience and adaptability of matter itself. Here is a world that was literally torn apart and rebuilt, that survived in the most hostile environment our solar system has to offer, and that continues to evolve and change even today. Its story reminds us that planets, like life itself, are not static monuments, but dynamic, ever-changing participants in the ongoing story of cosmic evolution. As you drift towards sleep tonight, perhaps you'll carry with you the image of Mercury in its earliest days, a larger, softer world, orbiting in the chaotic nursery of the young solar system, unaware that it would soon be transformed by forces beyond imagination into the small, dense, mysterious world that continues to surprise us today. In the grand theater of planetary formation, Mercury played a starring role in one of the most dramatic stories ever told, and we are only now beginning to appreciate the full scope of its cosmic performance. Now, as we drift deeper into Mercury's story, we arrive at one of the most captivating chapters in planetary exploration. For decades, Mercury remained largely mysterious, a distant world glimpsed only fleetingly through telescopes. But in recent years, we've begun to unlock its secrets through robotic emissaries that have journeyed across the solar system to whisper back Mercury's tales. The first messenger to visit Mercury was Mariner 10, launched in 1973 during an era when space exploration still felt like pure magic. This pioneering spacecraft performed 3 flybys of Mercury between 1974 and 1975, offering humanity its first close-up views of the innermost planet. The images revealed a heavily cratered, moon-like surface, scarred by billions of years of cosmic bombardment. Mariner 10 mapped about 45% of Mercury's surface, discovering the massive Calorus Basin and providing our first hints of the planet's unusual magnetic field. But like a tantalizing preview of a much longer story, Mariner 10 left many questions unanswered and vast regions of Mercury still shrouded in mystery. For over 3 decades, Mercury waited patiently for its next visitor. Then came Messenger, the Mercury surface, space environment, geochemistry, and ranging mission, launched in 2004 on an epic 7-year journey to Mercury's orbit. The name was fitting. This spacecraft truly was Mercury's messenger, carrying news of the planet back to Earth in unprecedented detail. Messenger's journey to Mercury was itself a marvel of celestial choreography. Mercury's proximity to the Sun makes it incredibly difficult to reach, requiring a spacecraft to shed enormous amounts of orbital energy. Messenger accomplished this through a series of gravity assists, flying by Earth once, Venus twice, and Mercury 3 times before finally settling into orbit around the planet in 2011. It was like learning to dance with gravity itself, using the gravitational pull of planets as stepping stones across the solar system. Once in orbit, Messenger revolutionized our understanding of Mercury. The spacecraft carried 7 sophisticated instruments that studied every aspect of the planet, from its surface composition to its magnetic field, from its thin atmosphere to its internal structure. Over 4 years of orbital operations, Messenger took more than 270,000 images, mapping Mercury's entire surface in stunning detail and revealing a world far more complex and dynamic than anyone had imagined. One of Messenger's most surprising discoveries was definitive proof of water ice at Mercury's poles. Using its neutron spectrometer and laser altimeter, the spacecraft detected hydrogen-rich deposits in permanently shadowed craters near Mercury's north and south poles. These deposits, estimated to contain between 100 billion and 1 trillion tons of water ice, exist in regions where temperatures remain below -300 degrees Fahrenheit, cold enough to preserve ice for billions of years despite Mercury's scorching equatorial temperatures. But the ice wasn't alone. Messenger also detected organic compounds, carbon-based molecules that could potentially serve as building blocks for more complex chemistry. The discovery was profound here on a planet that experiences some of the most extreme temperature variations in the solar system. In shadowed polar regions that never see sunlight, conditions exist that could preserve both water and organic materials. It's a reminder that even in the most unlikely places, the universe finds ways to harbor the ingredients of complexity. Messenger also revealed Mercury's geological dynamism. The spacecraft discovered evidence of recent volcanic activity, with some volcanic plains appearing to be only a few 100 million years old, relatively young in planetary terms. Smooth volcanic plains cover about 40% of Mercury's surface, suggesting that the planet experienced extensive volcanism throughout much of its history. The spacecraft also found evidence of explosive volcanism, with pyroclastic deposits scattered across the surface, indicating that Mercury's interior once contained significant amounts of volatile materials. The mission provided new insights into Mercury's unusual magnetic field as well. Unlike Earth's magnetic field, which is generated by convection in the liquid outer core, Mercury's magnetic field appears to be generated in a thin shell at the top of the core. This discovery suggests that Mercury's core is highly differentiated, with different regions having different properties and behaviors. The magnetic field, though much weaker than Earth's, still manages to create a small magnetosphere that provides some protection from the solar wind. Perhaps most remarkably, Messenger revealed that Mercury is still geologically active. The spacecraft observed evidence of ongoing contraction as the planet continues to cool and shrink, creating fault scarps and wrinkle ridges across its surface. Some of these features appear to cut through relatively young craters, suggesting that Mercury's geological evolution is still ongoing. It's a world that continues to reshape itself, albeit slowly, even after 4.6 billion years of existence. As Messenger's fuel supplies dwindled in 2015, the spacecraft was deliberately crashed into Mercury's surface, adding one final crater to the planet's collection while ensuring it wouldn't become space debris. But Mercury's story of exploration was far from over. In 2018, the European Space Agency and the Japan Aerospace Exploration Agency launched Bepi-Colombo, the most ambitious Mercury mission ever attempted. Bepi-Colombo is actually two spacecraft in one: the Mercury Planetary Orbiter, built by ESA, and the Mercury Magnetospheric Orbiter, built by JAXA. This dual spacecraft approach will allow scientists to study Mercury's surface, interior, and magnetic environment simultaneously, providing a comprehensive view of the planet's complex systems. The mission will investigate Mercury's magnetic field in unprecedented detail, study the planet's exosphere, map its surface composition with greater precision than ever before, and probe the mysteries of its large iron core. The journey to Mercury is long and complex, requiring 9 planetary flybys over 7 years to reach the planet. Bepi-Colombo has already performed flybys of Earth and Venus, and will make 6 flybys of Mercury itself before finally entering orbit in late 2025. Each flyby provides opportunities for scientific observations and helps refine our understanding of Mercury's properties. When Bepi-Colombo arrives, It will address some of the most fundamental questions about Mercury. How did such a small planet maintain geological activity for so long? What processes shaped its surface and continue to modify it today? How does its magnetic field interact with the intense solar wind so close to the Sun? What can Mercury's composition tell us about the formation of the inner solar system? The mission will also search for additional evidence of water ice and organic compounds, potentially mapping these deposits in greater detail and understanding their origins. Did they arrive via comet and asteroid impacts? Or could some represent indigenous materials for Mercury's formation? The answers could provide insights into how water and organic materials were distributed throughout the early solar system. These missions to Mercury represent more than just planetary science. They're journeys of human curiosity and ingenuity. Each spacecraft that ventures to Mercury carries with it our desire to understand our place in the cosmos, to comprehend the full family of worlds that orbit our Sun. They're technological marvels that push the boundaries of engineering, navigating the intense radiation and extreme temperatures of the inner solar system to bring back knowledge that expands our understanding of planetary formation and evolution. The data from these missions continues to reshape our understanding not just of Mercury, but of planetary processes throughout the solar system. Mercury serves as a natural laboratory for studying how planets form and evolve under extreme conditions. Its proximity to the Sun provides insights into how stellar radiation affects planetary atmospheres and surfaces. Its large iron core offers clues about planetary differentiation and magnetic field generation. As we prepare for Bepi Colombo's arrival at Mercury, we stand on the threshold of new discoveries. Each mission to Mercury has revealed that the planet is far more complex and fascinating than previously imagined. What surprises await us as we study Mercury with ever more sophisticated instruments? What new insights will emerge about this remarkable world that has endured the Sun's fierce embrace for billions of years? The story of Mercury exploration is ultimately a story about the power of human curiosity and our endless desire to explore the unknown. In sending our robotic ambassadors to Mercury, we extend our senses across the solar system, touching distant worlds and bringing their secrets home. Through these missions, Mercury transforms from a distant point of light into a real world with its own unique history, geology, and mysteries waiting to be solved. As Mercury completes another swift lap around the Sun, carving its eccentric path through space at speeds that would make your morning commute seem leisurely, we find ourselves approaching the end of our cosmic journey together. We've traced Mercury's wild ride from its formation in the furnace of the early solar system to its current role as both a planetary puzzle and a natural laboratory for testing the very foundations of physics. But Mercury's story is far from over. In fact, we're living through one of the most exciting chapters in Mercury science right now. The European Space Agency's Bepi Colombo mission, launched in 2018, is currently making its way toward Mercury through a complex series of gravitational slingshots around Earth, Venus, and Mercury itself. When it arrives in 2025, it will deploy not one, but 2 spacecraft into Mercury's orbit, providing the most comprehensive study of the planet we've ever attempted. Bepi Colombo represents a new generation of Mercury exploration. Where Messenger was primarily focused on mapping and basic characterization, Bepi Colombo is designed to dig deeper into Mercury's mysteries. One spacecraft will study the planet's surface and interior structure with unprecedented detail, while the other will focus on Mercury's magnetosphere and its interaction with the solar wind. Together, they'll help us understand not just what Mercury is like today, but how it came to be the way it is. The mission carries instruments that will peer beneath Mercury's surface using radar, analyze the composition of its thin atmosphere in real time, and monitor the planet's magnetic field with exquisite precision. It will search for water ice in permanently shadowed craters at the poles, investigate the strange hollows scattered across the surface, and study the planet's core to understand why Mercury has a magnetic field when Mars and Venus do not. But perhaps most intriguingly, Bepi Colombo will help us understand Mercury's role in the broader story of planetary formation and evolution. The planet's unusual properties, its high density, its eccentric orbit, its mysterious magnetic field, all point to a complex history that may hold clues about how rocky planets form and survive in the inner regions of stellar systems. This has implications far beyond our own solar system. As we discover thousands of exoplanets orbiting other stars, many of them small, rocky worlds in tight orbits around their host stars, Mercury becomes our closest analog for understanding what these distant worlds might be like. The extreme conditions Mercury experiences, the way it interacts with intense stellar radiation, the processes that have shaped its surface and interior over billions of years, all provide a template for understanding planets in similar situations throughout the galaxy. Mercury also continues to serve as our most precise test of Einstein's general relativity. The planet's orbit precesses by 43 arcseconds per century, more than Newton's laws predict, and this tiny discrepancy was one of the first confirmations of Einstein's revolutionary theory of gravity. Today, we can measure Mercury's orbital motion with such precision that it provides ongoing tests of not just general relativity, but alternative theories of gravity and the fundamental constants of physics. As our instruments become more sensitive and our understanding deepens, Mercury may reveal even more subtle effects that could point toward new physics beyond our current theories. The planet's extreme environment, where temperatures swing from over 400 degrees Celsius to minus 170 degrees, where the solar wind is intense and the gravitational field is strong, creates conditions that simply don't exist anywhere else in our solar system. There's also the tantalizing possibility of finding life-related chemistry on Mercury. While the planet's surface is certainly too extreme for life as we know it, the discovery of water ice at the poles and organic compounds in the planet's thin exosphere suggests that even in such hostile environments, complex chemistry can occur. Understanding these processes could inform our search for life in other extreme environments, both in our solar system and beyond. Looking even further ahead, Mercury might one day play a role in humanity's expansion into the solar system. The planet's proximity to the Sun makes it an ideal location for solar power generation on a massive scale. Its lack of atmosphere means that spacecraft can orbit close to the surface without atmospheric drag, and its low gravity makes it relatively easy to launch materials into space once you've landed there. Some visionaries have even proposed using Mercury as a source of raw materials for building massive solar power satellites, or as a stepping stone for missions to the outer solar system. The planet's iron-rich composition could provide the materials for spacecraft and habitats, while its position close to the Sun offers abundant energy for industrial processes. But perhaps the most profound aspect of Mercury's future story is what it tells us about time and change in the cosmos. Mercury has been following its swift, eccentric orbit for over 4 billion years, experiencing millions of these extreme temperature cycles, slowly cooling and contracting, its surface being constantly modified by micrometeorite impacts and the relentless pressure of solar radiation. Yet Mercury endures. It continues its faithful dance around the Sun, a testament to the fundamental stability that underlies the apparent chaos of planetary motion. In a universe where galaxies collide, stars explode, and black holes devour entire solar systems, Mercury's clockwork precision reminds us that there are islands of predictability in the cosmic storm. The planet has witnessed the entire history of complex life on Earth. Every dinosaur that ever lived, every human who ever drew breath, every story ever told has unfolded while Mercury completed its relentless 88-day cycles around the Sun. It was there when the first life emerged in Earth's oceans, when the first plants colonized the land, when our ancestors first looked up at the night sky and wondered about the wandering stars. And Mercury will likely still be there long after our current chapter of the cosmic story has ended. The sun will gradually brighten over the next billion years, making Earth uninhabitable. But Mercury, already adapted to extreme heat, may continue its orbital dance relatively unchanged. Eventually, in about 5 billion years, the sun will expand into a red giant, and Mercury's story will finally come to an end as it spirals into the bloated outer layers of our dying star. But that's still an unimaginably long time in the future. For now, Mercury continues to surprise and delight us with its contradictions and mysteries. It's a world of extremes that somehow manages to be stable, a tiny planet that packs the gravitational punch to test our most sophisticated theories, a barren rock that may hold clues to the origins of life itself. As you drift off to sleep tonight, perhaps you'll spare a thought for Mercury, racing through its eccentric orbit somewhere in the darkness above. In the time it takes you to sleep through the night, Mercury will have traveled nearly 1 million kilometers in its path around the sun, experiencing temperature swings that would melt lead and freeze nitrogen, all while maintaining the precise gravitational ballet that has kept our solar system stable for billions of years. It's a reminder that even in sleep, even in the quietest moments of our lives, the universe continues its grand performance. Planets wheel through their orbits, stars burn in the darkness, and somewhere out there, a small, dense world named for the messenger of the gods continues its wild ride around the sun, carrying with it the secrets of planetary formation, the testing ground for our theories of space and time, and perhaps, just perhaps, clues to questions we haven't even thought to ask yet. Sweet dreams, fellow travelers. Mercury will still be racing when you wake. Looking back on our journey through Mercury's wild cosmic dance, we find ourselves at a fascinating crossroads where the smallest planet in our solar system offers some of the biggest lessons about the universe itself. We've traced Mercury's breakneck 88-day orbit, marveled at its peculiar 3-to-2 spin-orbit coupling, and witnessed how this tiny world has become an unexpected laboratory for testing the very foundations of physics. From the scorching plains of the Caloris Basin to the frozen water ice hiding in polar shadows, Mercury continues to surprise us with its contradictions. Here is a world where noon temperatures could melt zinc while midnight brings Antarctic cold, where massive iron cores generate whisper-weak magnetic fields, and where organic compounds somehow survive in one of the most hostile environments imaginable. The missions that have visited Mercury, from Mariner 10's first glimpses to Messenger's detailed surveys and Bepi Colombo's ongoing investigation, have revealed that our understanding of planetary formation and evolution still has vast, unexplored territories. Mercury's oversized core challenges our models of how rocky planets form. Its magnetic field hints at dynamic processes we're only beginning to comprehend. Its surface, scarred by billions of years of impacts and volcanic activity, tells stories of the early solar system's violent youth. But perhaps most remarkably, Mercury has become a testing ground for Einstein's theories of space-time. The planet's perihelion precession, that subtle advance of its closest approach to the sun, provided one of the first confirmations of general relativity. Every orbit Mercury completes is a small experiment in fundamental physics, demonstrating how massive objects curve space-time itself. As we peer into the future of Mercury research, new questions emerge with each answer we uncover. How did such a small world retain so much internal heat? What processes shaped its unique magnetic field? Could the organic compounds in its polar regions teach us about the delivery of life's building blocks throughout the solar system? And what will Mercury's eventual fate be as the sun evolves and expands? These questions remind us that even in our own solar system, even with our nearest planetary neighbors, mystery and wonder persist. Mercury, racing endlessly around our star in its wild elliptical dance, carries within its cratered surface and hidden depths the keys to understanding not just our own cosmic neighborhood, but the countless exoplanetary systems we're discovering throughout the galaxy. So as Mercury continues its eternal sprint around the Sun, completing another orbit every 88 Earth days, it remains both familiar and foreign, tiny yet significant, simple in its solitude yet complex in its secrets. In studying Mercury, we study ourselves, our origins, and our place in the vast cosmic symphony where even the smallest players can carry the most beautiful and mysterious melodies. The smallest planet has taught us that in the cosmos, size matters far less than story, and Mercury's story is still being written with each passing orbit, each new discovery, each quiet revolution around our star. As we near the end of our cosmic journey through Mercury's extraordinary dance around the Sun, it's worth pausing to appreciate just how much this little world has taught us about the universe itself. Mercury may be the smallest planet in our solar system, but its influence on our understanding of physics, planetary formation, and the cosmos extends far beyond its modest size. You see, Mercury isn't just a hot, cratered rock whipping around the Sun at breakneck speed. It's a laboratory, a testing ground for some of the most fundamental theories that govern our universe. When Einstein proposed his theory of general relativity in 1915, one of the most compelling pieces of evidence came from Mercury's orbit. The planet's perihelion, the point in its orbit closest to the Sun, precesses or shifts slightly with each orbit in a way that Newton's laws of gravity couldn't fully explain. Einstein's equations, however, predicted this precession with stunning accuracy, providing one of the first confirmations that our understanding of space, time, and gravity needed a revolutionary update. This tiny discrepancy in Mercury's orbit helped validate one of the most profound scientific theories ever conceived, reshaping our understanding of the very fabric of reality. It's remarkable to think that a planet you could fit inside the United States with room to spare played such a crucial role in confirming that space and time are woven together, that massive objects bend this space-time fabric, and that gravity isn't a force pulling objects together, but rather the curvature of space-time itself. But Mercury's contributions to science extend far beyond relativity. The extreme conditions on this world have taught us about planetary formation in ways no other planet could. Its enormous iron core, taking up about 3/4 of the planet's radius, tells us a story of violent collisions and cosmic catastrophes in the early solar system. The leading theory suggests that Mercury once had a much thicker rocky mantle, but a colossal impact early in its history stripped away much of this outer layer, leaving behind the metal-rich world we see today. This catastrophic origin story isn't just Mercury's tale, it's a window into the chaotic, violent birth of our entire solar system. The planets didn't form in the neat, orderly fashion we might imagine. Instead, they emerged from a swirling disk of dust and gas through countless collisions, near misses, and gravitational interactions. Mercury, with its oversized core and thin mantle, bears the scars of this tumultuous period, a permanent reminder of the forces that shaped all the worlds in our cosmic neighborhood. The planet's extreme temperature variations, from over 400 degrees Celsius on the day side to minus 170 degrees Celsius at night, have taught us about atmospheric dynamics and heat transfer in ways that inform our understanding of exoplanets. Many of the planets we've discovered orbiting other stars are tidally locked like Mercury, with one face permanently turned toward their star. By studying how Mercury manages its extreme temperature differences, we gain insights into the potential habitability and atmospheric conditions of these distant worlds. Mercury's magnetic field, weak though it may be, has revealed secrets about planetary magnetism and the deep interior dynamics of rocky worlds. The fact that such a small planet can maintain any magnetic field at all suggests that its core is at least partially molten, an unexpected finding that has implications for our understanding of how planetary cores evolve over billions of years. This magnetic field, interacting with the solar wind, creates Mercury's thin exosphere and contributes to the complex particle environment around the planet. Perhaps most surprisingly, Mercury has taught us about water and the potential for preserving organic compounds in the most unlikely places. The discovery of water ice in permanently shadowed craters at Mercury's poles was a revelation that challenged our assumptions about where water can exist in the solar system. If water can survive on Mercury, the planet closest to the Sun, then it might be more common throughout the solar system than we ever imagined. The organic compounds found alongside this water ice add another layer of intrigue. These carbon-based molecules, the building blocks of life as we know it, have somehow survived in Mercury's polar regions despite the planet's proximity to the Sun's radiation. This discovery has implications for astrobiology, the study of life in the universe, suggesting that organic materials might be preserved in cold traps throughout the solar system, waiting to be discovered. Mercury's geological features, from the enormous Calorus Basin to the mysterious hollows that dot its surface, have revealed the complex interplay between impact processes, volcanic activity, and space weathering. The planet's heavily cratered surface preserves a record of the early solar system's bombardment history, while features like the lobate scarps tell us about Mercury's thermal evolution and how the planet has shrunk as its interior cooled over billions of years. The ongoing Bepi-Colombo mission promises to deepen our understanding even further. This ambitious joint mission between the European Space Agency and the Japan Aerospace Exploration Agency will study Mercury's magnetic field, internal structure, surface composition, and exosphere in unprecedented detail. The data from Bepi-Colombo will help us refine our models of planetary formation, magnetic field generation, and the evolution of rocky worlds. Looking ahead, Mercury continues to serve as a crucial benchmark for testing our theories and models. As we discover more exoplanets, particularly those in close orbits around their stars, Mercury provides a nearby example of how rocky planets behave under extreme stellar irradiation. The lessons learned from Mercury inform our search for potentially habitable worlds and help us understand the diversity of planetary environments in our galaxy. Mercury also plays a practical role in our exploration of the solar system. The planet's strong gravitational field and proximity to the Sun make it an ideal location for gravity-assist maneuvers, helping spacecraft gain speed and change direction as they journey to other destinations. Future missions to the outer solar system will likely use Mercury's gravity to slingshot toward their targets, making this small world a crucial waypoint in our exploration of the cosmos. As we stand on the threshold of a new era in space exploration, with missions planned to asteroids, Mars, and the outer planets, Mercury remains a touchstone for our understanding of planetary science. Its extreme environment pushes the boundaries of what we know about rocky worlds, while its proximity makes it accessible for detailed study in ways that distant exoplanets are not. The story of Mercury is ultimately a story about the power of scientific inquiry and the unexpected ways that knowledge unfolds. Who could have predicted that the smallest planet in our solar system would play such a pivotal role in confirming Einstein's theory of relativity? Who would have guessed that this scorched world would harbor water ice and organic compounds in its polar regions? Science is full of such surprises, reminding us that the universe is stranger, more complex, and more wonderful than we can imagine. Mercury's wild ride around the Sun continues, as it has for billions of years and will for billions more. Every 88 days, this remarkable world completes another orbit, racing through space at speeds that would make even the fastest human-made objects seem sluggish by comparison. Its elongated orbit carries it from the relative coolness of aphelion to the furnace-like heat of perihelion, subjecting the planet to forces and conditions that no other world in our solar system experiences. And perhaps that's the most beautiful thing about Mercury. In a solar system filled with diverse and fascinating worlds, each with their own unique characteristics and stories, Mercury stands apart as the ultimate extremophile planet. It doesn't just survive in conditions that would destroy most other worlds, it thrives, maintaining its complex systems and revealing new secrets with each passing year. So the next time you look up at the evening or morning sky and catch a glimpse of Mercury, that bright wandering star hanging low on the horizon, remember that you're looking at one of the most important teachers in our solar system. This small, swift world has helped us understand gravity, time, space, planetary formation, and the potential for water and organic compounds to survive in the most unlikely places. Mercury's journey around the sun is far from over, and neither is our journey of discovery about this remarkable world. As our technology improves and our missions become more sophisticated, Mercury will undoubtedly continue to surprise us, challenge our assumptions, and expand our understanding of the universe we call home. In the grand cosmic dance of planets and stars, Mercury may be small, but its contributions to human knowledge are immeasurable, a testament to the power of curiosity, exploration, and the endless capacity of the universe to amaze and inspire us. The sleepy scientist in all of us can rest easy knowing that somewhere out there, Mercury continues its eternal dance, keeping perfect time with the cosmos and waiting patiently to reveal its next secret to those bold enough to seek it.